Good evening, and welcome to the scientific adventures of Beardman. Today we're going to be looking at refraction, which is what happens to light as it enters a new medium. But what lies behind the principle of refraction is the fact that light travels at different speeds in different materials, in different media, just like we saw with mechanical waves. With light, we know that it travels at a speed of 3.00 times 10 to the 8th meters per second in a vacuum, and we said that it was very close to that in air. But when we start to get to things that are more optically dense, is the technical word, but that have more molecules closer together, something happens and it slows down the molecules. Probably the best way to explain why they slow down is as follows. As the light, a photon, is traveling from one molecule to another, it travels at the speed of light, c, 3.00 times 10 to the 8th meters per second. But when it gets to a molecule, because a photon is an electric field changing and magnetic field changing, when that electric field reaches an atom or molecule, well, there are electrons in there that have some ability to move around, and so as that electric field moves, it will start to move the electrons. And as those electrons move, that will produce an electric field that opposes the one that created it, and so forth. But then it'll reach a vibrational state that it can't maintain because of quantum mechanics, something we don't really want to get into, and so you could say it re-emits the light. You could say it kind of slows it down as it passes through, or you could say it re-emits it because of the quantum mechanical nature of it. Neither one is completely correct and neither one is wrong, so to speak, or they're both a little bit wrong. Anyways, but that's a good way to think about it, is it's kind of making a speed of light journey to the next molecule, which then it takes a little while until it moves on to the next molecule. So one way to think of this is, remember, like some things like my shirt absorb the red and green light, but the blue light is reflected. Well, the molecules can't absorb the blue light. Okay, so just think of it like this. An air molecule or a water molecule can't absorb visible light, at least most visible light, and so it will, when the photon hits that molecule, it may make it vibrate for a moment, but it can't absorb it. It doesn't have the right energy levels to absorb it, and so that much energy can't be absorbed by that molecule, and so it will be re-emitted and carried on. Once again, traveling at the speed of light in between the molecules, but getting slowed down as it's passing through a molecule is probably the best way to say that. So that makes it travel slower in different substances. For example, in water, it takes 33% longer to get through the same amount of water as if it was going through that amount of a vacuum or that amount of air. It takes 50% longer to get through a piece of glass, and it takes 150% longer to get through a diamond. Okay? All of these come into something we call the index of refraction of a material. Okay, so a vacuum is 1.00. Okay, that's the index of refraction of a vacuum. The index of refraction of water is 1.33. Glass is 1.5 to 1.6, depending on the type of glass. And a diamond is 2.5. Okay, and that's essentially telling us how much slower it goes than the vacuum. Okay, or how much longer it takes to get through things than the vacuum. So what happens when light hits a boundary? Okay, well, if light's traveling along, okay, and it gets to a boundary, it's traveling through the air and it's about to go into the water, and it's traveling along perpendicular to it, well, it just goes right in. Okay, it slows down as it goes into the new medium because now it has to get through the molecules. It has to be absorbed and re-emitted, or however you want to explain that. Okay, so as it goes through, it slows down. But if it's going perpendicular, well then all the parts of that wave front, okay, as the wave hits it, all the parts of it slow down at the same time, so it just keeps going, just slower. Okay, but if it hits it at an angle, well then one part of that hits the new medium first, and it will slow down before the other part. The other part's still traveling fast, traveling through the air. Okay, and so this part will slow down first, which in order to keep up with, or in order to stay with the other parts of the wavefront, it's going to cause it to bend. Okay, the best way to think of this is, well, the way I like to think of it is if you picture like taking a dolly for moving refrigerators, or you could stack boxes on a roll. It's got two wheels, okay, and you're pushing that dolly along the cement. When you get to the grass, if you're going straight onto the grass, both of the wheels hit the grass. It slows down, and if you aren't careful, it slows down too much and you run into it, okay? But it slows down the whole thing at the same time. But if you're going at an angle and one wheel hits the grass or the sand or whatever it's going to travel slower in, all of a sudden it's kind of jerked sideways. The wave or the dolly is jerked sideways because this wheel is traveling slower than this wheel, and so this one's going faster, so it kind of takes the outside of the turn, so to speak, and it turns the whole dolly. Okay, same thing's true of cars. You may have learned this in driver's training, that if you're driving along on a freeway and you've got to pull off onto gravel, you have to be very careful and hold really stiffly on the steering wheel, because your right tire here in the United States, it'd probably be your left tire in England, okay, but your right tire is going to hit that gravel first, and it's going to slow down. Okay, as it hits it, it travels slower through the gravel, and so it's going to slow down, and that's going to kind of make your car begin to turn. Okay, all those are to explain and help you understand that as a light comes in, really any wave, but right now we're dealing with light, as a wave comes into a boundary between a medium where it travels faster to a medium where it travels slower, that side is going to turn. It's going to turn the wave. Okay, as we see in this picture traveling from air into water, when the light gets there, it's going to bend. That bending is called refraction. Okay, finally, 5 minutes in, we finally get to the title of the video. So the refraction is that bending of light caused by the fact that the light travels slower in one of the mediums, and therefore when one side of a wave gets there first, that makes it a bend. Okay? Now, we have a way to calculate this. It's called Snell's law. And basically, if we take the angle of incidence, measured similarly to how we measured the angle of incidence with a mirror, we take the boundary, we find the normal to the boundary, and we measure the angle between the ray of incidence and the normal, and that angle, as you see marked here, is the angle of incidence. The angle of refraction is similar to the angle of reflection, except of course in reflection it's heading back along the same, on the same side of the boundary, and so we're using the same normal, you might say, but now it's passing through, so we're using a normal on the other side of the boundary, so in the water in this example. So as the light goes from the air into the water, now we got the normal there, here's our ray of refraction, and so the angle between those is the angle of refraction. So our equation to combine these two things is the index of refraction, signified by a lowercase n, of the incident material times the sine of the incident angle equals the index of refraction of the material the wave enters into, the refracted index, you could say, times the sine of the angle of refraction. Okay, notice that one thing about this equation is it doesn't really matter which one is incident, which one's refraction, because they're identical on both sides. In other words, if the light comes in here and bends like this, if we went the exact opposite route up, it would follow the exact same path in the light, in the air. So as it comes in and bends one way, it would do the exact opposite, traveling the other way through the boundary. One example of this that you see very commonly is a straw in a glass of water. You take a look at that straw. You can see it in the picture here. As we look at that straw, the light leaving the straw is getting bent as it comes out of the water. And so we see the light where it's coming at us. And so that's where we interpret the straw being. Our brain doesn't interpret that the straw is really over here, and the light started here and headed towards the edge of the cup, but then got bent to us. We just see it where the light is coming from. Okay? And so that's why when you're looking into a cup of water or into a fish tank or whatever it might be, the fish isn't exactly where you think it is, or the straw isn't exactly where it looks like it is, because of the refraction. Okay? One other place you can see refraction, people often call them heat waves rising off of the lone desert highway. I feel the wind in my hair, the warm smell of colitos rising up in me. Anyways, so driving along the road out in the middle of the desert, the ground gets very hot. That hot air is less dense, and so it begins to rise. As it rises, if a light ray coming off the road or off a cactus or whatever goes through hotter air, well, that hotter air has a different index of refraction than the cold air, and so that makes the light bend. And so the part of the road we thought that is over there, that light appears to be over here now, and as the hot air is rising, it's constantly shifting where stuff looks, and that's why you get that wavy look off in the distance on a hot summer day along the freeway. People often call them heat waves. It's just the air heating up and the light being refracted through it. Okay? Stars actually twinkle for a similar reason. As the light comes through the atmosphere and they reach different parts of the atmosphere, the light gets refracted differently. Depending on what type of air is blowing overhead at the moment, the light gets bent around a little bit as it's entering new media from cold air to warmer air as it's on its way down. Another example of refraction is a magnifying glass. It bends the light coming into it and focuses it so we think it's bigger than it really is. And that's another example of refraction. And that is the concept behind refraction, the bending of light as it travels from one medium to another. All right, hope you enjoyed that. Look for examples of refraction in life where when you're looking into a new medium and something doesn't appear where you expected it to be. All right, we'll see you next time on the Scientific Adventures of Beardman. Have a great day.